Hello viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about core of reality, aka Delta T. So let's dive deep into it. Now, first thing you have to understand, this is the law, and I do not mean human-made laws that change. No, this is the law. We discovered it. So this is reality governed by certain laws, like action equals reaction. That's the law. Same thing happens here. Now, why should you bother with it? Now, here's the deal. I'm not talking about the mathematics of it. And knowing that mathematics will help you, but I want you to fundamentally understand the core of it. Basically, think in this way. If you have the foundation, you can build a building on it using mathematics. But if you have the foundation, at least somebody can't troll you. And again, we need to know this. So it will allow you to see the action that is happening in your real life. And I mean in every domain. Why your air conditioner is consuming so much power, why your car mileage is lower. Everything will make sense if you understand this foundation. And thermal energy is the fundamental to reality. Like, most things are thermal driven, like almost everything. Now, yes, there is electricity also, but thermal is there. And your life depends on it. Like literally, your human body is a reactor, bioreactor that is reacting. It's dumping heat. And if you can't dump heat, you're dead. So fundamentally, everything relies on it. Planet, sun, cosmos, everything. So what's the rule? Rule is it must flow. So what is it? Energy must flow. So hot to cold, heat must flow. The end. That's the law. Heat must flow. Now, again, that's a simplified version of it. Scientists have worked very hard to define it scientifically. And yeah, that's complex. So we call it second law of thermodynamics. That will actually define it, what is going on, so to say. Now, to give you essence of it, how heavy this thing is. This is one of the only equations that does not work in backwards. Like, for example, if you can electrolyze the water, you can burn it, right? Like you can electrolyze the water, burn it, and then do it again. You can keep doing it. It's reversible. Thermodynamics second law allows, like, why can't we go back in time? It's called arrow of time. Like fundamentally, why universe is like, yeah, it's cooled down. Why it can't be heated up again? Yeah, it won't work that way. So it is significant. Again, you can dive deep into it. People spend PhDs on it to understand full depth of it. But it's one of those things that we figured it out. We put a name to it. We tested it extensively. And yeah, at this point in time, we're done. Like, it's going to hold up no matter what. If it's not, it may have some, like, other avenue of observation that you are missing. For example, you are looking at a bulb and it's like, oh, where the energy is going and all that is like, have you looked into infrared spectrum? So same thing. So T hot, as in your temperature hot side, TC, temperature cold side, equals work. How much useful work, 100% will be left, that will happen. But how much useful work you get out of it is defined by second law of thermodynamics. So let's dive deep into it. Now be mindful, when we are talking second law of thermodynamics, it's a what you call law of the universe. There is a lot of sub-laws that are encapsulated inside it. We just call it the daddy law, as in like second law of thermodynamics. So delta T, that's the engine of the world, so to say. Temperature difference, as also known as delta T, is the driving force. Basically, why does your car work? Delta T. Why does the coal power plant work? Delta T. Why does the nuclear plant work? Delta T. Everything is delta T. And you have to be mindful. It's basically heat flow from cold to hot. So gap between hot and cold matters more than the unit that you're talking. For example, the best example is, imagine a rocket engine. Imagine Saturn V. Cool, awesome. You have the best alloy known to man. Let's just say you figured out some sort of Inconel alloy. It's great. But here's the deal. It cannot handle 1000 degrees Celsius while remaining structurally sound. Like if you have 1000-degree flamethrower running continuously, yeah, it will become soft. Other metal would have melted long ago, but this would be like structural integrity. Even steel, steel melts at higher, anything melts higher. It's like structural integrity at high temperature. That's the magical alloy part. So you have a limit, but you need a rocket engine. How the heck you gonna go to moon if your rocket engine melts itself? Somebody figured out T delta, that aka while the metal that is around the fire can't handle, like let's just say raw 1500 or 2000 degrees Celsius heat, it can easily tank 600 degrees Celsius heat or 700 degrees Celsius. So they're like, hey, we have a what we call a gas generator that is driving the turbine. The exhaust of it is very unburnt, so it's not clean, it's cold. How cold? 700 degrees Celsius. So they flow it inside the bell nozzle to insulate the hot fire. Again, relative temperature. You want your metal to be below 700 degrees Celsius. Cool. You have a gas cooling layer that is 600, and then you have a fire that is 1500 plus degrees Celsius. And same rule, encapsulating something very hot into something mildly hot is done by jet engine. That's why your jet engine does not melt while it's in the air, because it has the, you might be like, okay, turbine can handle it, but again, turbine blades are the only thing. What about the chamber? How the heck the chamber is cooled? Yeah, chamber has bleed air. Air is bleed. Now be mindful, while bleed air is classified as cooling air, it's not cold. It's not 0 degrees Celsius, even though it's like at high altitude, it could be breathing in as low as like, let's just say minus 20 degrees Celsius. By the time it goes through the compression stage, it could be as hot as like 300 to 400 degrees Celsius. So, but again, that temperature metal is like, I got you, fam. So this is the whole aspect. It's differential that matters, not the what you call absolute temperature. Unit also does not matter that much, like degree Celsius, degree Fahrenheit, or Kelvin. Like if you want to understand, Fahrenheit is weird. Kelvin is basically cooler version of Celsius. Celsius has the penalty that math goes wrong because it has negative symbols. Does not make sense. There is no cold. So why do you have a negative number when there is no cold? So they're like, okay, let's take the Celsius centigrade scale and shift it downwards. Basically, they removed the negative symbol and that became Kelvin. So there is 0 Kelvin. There will never ever be minus Kelvin. You can go 0 Kelvin. You cannot go minus Kelvin. Penalty? Yeah, your room temperature is 300 degree Kelvin. So that's why I said like the T delta matters more than these units, because again, if you know your units or conversions right, it will make no difference. Generally, for our simplicity and sanity sake, we do most math in Kelvin. Again, I told you, maths should not be wrong. So you cannot have negative temperatures because there is no negative temperature. It's only 0 or hotter. So difference is the only thing that matters. You have to fundamentally understand that. So I'm pretty sure most of you have went to school and you must have done an experiment known as Newton law of cooling. Now be mindful, this Newton law of cooling is very what you call observational reality rather than absolute fact. It's almost like a 2 megapixel photo. Like Newton came up with gravity. It's like, yeah, but like the photos were very low resolution, like 2 megapixel. Einstein comes along, it's like, bro, I got this, that's good, but let's define it. Let's 24 megapixel. That's what we call basically space-time continuum or general theory of relativity. So same thing happens with this also. So Newton's law of cooling is just explained as a more of a getting you used to the idea rather than like the science, the raw science, because again, you're supposed to study second law of thermodynamics, not Newton's law of cooling. But this is a very good intuition that you must develop, and that's why you must have done the experiment where you have a water beaker, generally with a small water heater that heat it up to whatever temperature. Generally, if they are comfortable with 45 degrees Celsius, 45 degrees, you pull out the heater and then you plot a graph. Basically, every minute you write down the thermometer temperature. Back in my day, we used to have that like mercury thermometer. We used to write it down and then you plot it. It will come out to like, okay, there was a bit of a noise, and nowadays it's super easy. You can do with Arduino. But once you see this curve, like your mind will like, oh, that's why everybody is so keen on eating very hot food in India. I have no idea what Americans do, but in India, you want super duper hot food. And it never made sense to me. I'm not that sensitive. Either my tongue will burn or I will not know. So it was like, okay, why? But here's the deal. The moment food is out of the stove, like let's just say hot tea, we want flaming hot tea in summer. So that hot tea, when it's out of the stove, it's very hot. Let's just say 60 degrees Celsius. It will drop to 40 degrees Celsius in a few seconds. Like you have to be very quick with it. So people want that instant, boom. And that's why you can pay attention to luxurious 5-star hotels or like, you know, prime real estate hotels. They generally have a hot plate in the table itself. So when the chef actually, you know, puts out the food from the flame, it goes on an unheated system and goes onto a heated system. So this does not drop that much. You'd never want the temperature to go here, even though it's still hot. And again, a child without thinking, eating it, it will burn itself, but it won't be that hot. And again, that's why you have to do this, what you call Newton's law of cooling. It will fundamentally give you the ideas, like why things cool down from high temperature to mid temperature very quickly. Mid to low is very hard. Inherently, like this happens to everything. Your soldering iron, your basically, if you are dealing with, let's just say, vaccine refrigerators, those require like minus 80 degrees Celsius. You will turn it on, it will drop the temperature in negative very quickly. It's like, okay, you turn it on, let's say room was 25 degrees, it's like, okay, 10 degrees Celsius, damn, 20 degrees Celsius, damn, it's going fast. And then it will take, in 15 minutes, it took 0 degrees Celsius. 1 hour later, minus 10. 4 hours later, it will go down to that sort of, it might even take 1 day or 2 days to cool down to that level. Again, same thing. Newton's law of cooling, it's a what you call very simplified too mega step, but it's a good thing for every child to understand inherently, because it applies to food, your body, everything. And then when you want to go to Big Daddy, as in like son, so you study Stephenford Boltzmann law. Now this is a law. This is the law. Like, this is a sloppy interpretation because again, this was observed reality when you have conduction and convection. This is vacuum. What if you have a reactor that is surrounded by vacuum, hard vacuum? There is a law. The law is this law. Power radiation, basically how much oomph is being generated. And this is a weird variable. This is very, what you call, linear even. Like, even though it looks like curve, it's almost linear. This puppy, yeah, this is mad. This has power of 4. As in, if you increase the T delta between it and the ambient, it multiplies by 4. Now, does that matters right now? Yes. NASA is building a nuclear powered reactor based system that is going to Mars. Cool, awesome. How the heck you gonna cool the reactor? Well, making it hotter. As in the radiator, if they are designing the radiator on Earth, they will target a temperature of 100 degrees Celsius maximum. But when you are in space, that is not good enough. But what if you made it 400 degrees Celsius? As long as your metal can handle it, because T to the power 4, you will dissipate massive amount of heat on a small surface area, even in vacuum. So this law allows you to understand that. So this, the whole aspect of delta T, is the difference between temperatures that matters the most. Again, different domain have a different feeling. For example, this will give you a better understanding of how things work on Earth. This will give you a better understanding of how space system works or space data centers. And again, that's why I'm laughing. Like, your CPU cannot go hotter than, like, 60 or 80 degrees Celsius for longevity reason. Let's just assume 80 degree, you're going all hard on it. That's not hot enough for this equation to really cool you down. You need like 300 or 400. So you need a heat pump, and then you need a second stage cascading heat pump. Only then you can have a radiator powerful enough where it can dump that much heat. Can you do that? Of course you can do that. Can you do that cheaply? No. No. So that's why delta T matters. Now that's the essence of it. How does it affect to your daily life? Power. We want unlimited power. And we do have that. Like, if you ever studied how much power is there in a barrel of oil or like in a ton of coal, you would be frustrated. It's like, dude, why the hell we have shortage of energy when we have this much energy? Yeah, that's because of delta T or this puppy. Hot source, aka the fire, and the cold sink, your radiator. That's it. And the useful work that you're going to get out of it. So we use heat to make power. That's the core of it. Does not matter the source. Source could be fission reactor, fusion reactor, it could be coal, it could be concentrated solar, it could be something else. Does not matter. Geothermal, it does not matter. Generally, source does not matter. It's the heat, and heat, specifically the temperature of that heat, matters. And Carnot efficiency is the law. This is the law. That's why I said all of these come under the second law. So Carnot efficiency is the law that is at play here. What does it say? It simply says how it should be hot. The hotter this is, the better you are. So this puppy has to be hot, like this. Or again, let's just say you are in a scenario. For example, let's just say you are landing on Mars and you're like, hey, we have a reactor, and reactor, because of the safety reasons and all that, like what we call NASA kilowatt reactor, you do not want the hot to be very hot. You want to be safe margin. So like, okay, we can't increase the 400 degrees Celsius. That's the temperature of liquid sodium heat pipes that they are using. Cool, awesome. But you can have the radiator cooler, dunk the radiator into dry ice. Ta-da! So those are two throttles. Like, that's why your car will give you a poor mileage in summer, because this is not cold enough. It is designed to, it's designed to work, it's designed to handle it, but it's not. And again, same thing happens at high altitude. You're like, okay, but like, I thought it was air. Generally, you have turbo to compensate for it. It's just that radiator cannot dump heat enough. And again, some of the vehicles that are designed for that, generally a bigger radiator. Because again, thinner air, it has to move a lot more air to dump same amount of heat. If cold reservoir does not go down enough, either you can overheat or you will lose efficiency. So both of that matters. Hot has to be hot, cold has to be cold. And that's why when you are on sea level, it's super easy because your radiator is working effectively. So you can cool the air by injecting nitrous into it, ethanol into it, or water into it. But in high altitude where air is cooler, your engine is like struggling because this has elevated. It can't dump heat. Even though it's cold, it can't dump heat. It's like there is not enough molecules. So fundamentally, that's the law. And that's why your jet engine has to scream at like stupid temperatures. Like the early jet engines, we started with 400 to 600 degrees Celsius. It barely worked, barely. And then we are like, okay, 1000. Now we are like 1500 degrees Celsius. The only reason we are keeping it at 1500, it's not because of the metal. We figured out how to keep it cool. It's just the issue is if we increase the temperature more, the NOx emission goes up. So they are like, yeah, no. And again, there is a Russian jet, bomber jet, that is very ugly in this regard. It has very high temperature. And how do you know that? Yeah, when it flies, there is a yellow soot, NOx coming out of it. Nitric acid, sorry. Like a yellow smooth, like, and you can see that in Saturn V. There's also SpaceX rocket launch. You'll see like a very weird yellowish, orangish glow that is sliding, but it's not using peroxide. So why the heck that is there? Yeah, atmosphere does not like a blow stick that big. So hotter is better, but again, atmosphere reactions is like, And again, you can see that in real life when we are burning coal, we are not just burning, we are burning it. Basic bitch coal power plants still burn their coal at 1200 degrees Celsius. The fire temperature, if you put a thermometer there, it will read 1200 degrees Celsius. Although your best case scenario, like if you are in Germany and going YOLO on coal power plant, that power plant, the turbine temperature, basically turbine inlet where they are getting the highest pressure, high temperature steam, that still would be only 600 to 700 degrees Celsius. And that number will go into this mathematics. It will not, like, you will not take 1600 of the fire into there. You will take the temperature of the turbine, because turbine is the converter, so to say. So that's why whenever people are like, oh, we have so much data center that is creating so much heat, why can't we use it? The heat is there. Megawatt of heat, that is there. That's more than good enough. It's just that this is not there. We do not have basically 0 Kelvin heat sink, and the hot is barely what, 70, 80, maybe 100 degrees Celsius. We need 1500. So, and again, this was also another issue with concentrated solar. On paper, this made sense. It's just that when we realized the temperature is not hot enough, like you would be lucky to get like 300 to 400 degrees Celsius. They tried everything. It's just like, and that's why, like, you know, you had linear concentrator, barely that temperature. Concentrated, really concentrating it. Yeah. So, and that's why this all got displaced with solar panels. It was just like, dude, I'm not working on heat. I'm working on photon flux. So it made more sense. That's the biggest hurdle with humanity. If we can figure out how to directly use low-grade waste heat, problem solved. For example, let's just say you are in a city, and let's just say city is not stupid. They have a district cooling system. You have a coal power plant. Okay, here's the deal. What if you use the waste heat, which is now at low delta, like this waste heat, it's at low delta. It would be just a bit more above than ambient. What if you use that heat to run a adsorption chiller or absorption chiller, and voila, you'll get cooling. But you're like, yeah, because again, T delta is low, the COP won't be very high. Coefficient of performance would be poor, but that's from waste heat, and you have so much waste heat, it does not matter the efficiency. Tada, it's what we call combined heat and power. In those sort of scenario, you can achieve much higher efficiency, like almost 60% conversion efficiency, meaning useful work is much higher. Like this useful work is much higher. And if you are in a scenario where you also need hot water for some reason, voila, you are almost hitting 90% efficiency. But again, direct mechanical conversion is not that high. It can never be that high. This is not high enough. And this is another primary reason why ORC, while it is awesome, we don't run solar concentration ORC in our rooftops to create electricity. It is very inefficient, 10-20% efficient. Be mindful whenever you're doing this calculation, you must do Kelvin calculation. That's why it was done. It will make your life much easier. Now we come to HVAC. That thing opposite is HVAC basically. All type of refrigeration system are a heat pump. I have no idea who was smoking in India when they created our 5-star system. It's our energy rating. It says heat pump yes or no, and I'm like, why all are heat pumps? Yes simply means like in my AC, this AC is heat pump. It can work in backwards, as in like a normal AC, or as a heater, as in like it will reverse the flow. The condenser will become the indoor unit, the evaporator will become the outdoor unit. It will work. So again, that's a very poor understanding of heat pump. I think they did it for public use. I hate it, but okay. So everything is heat pump. For example, your refrigerator, heat pump. Your AC, heat pump. A heat pump is a heat pump. Your adsorption chiller that takes fire to make ice, still heat pump. All of these are heat pumps. And we measure their efficiency in COP, coefficient of performance. And basically, how do you know how much work you put in to basically like your compressor, how much energy you put in, let's say 1 unit of electricity, 1 kilowatt hour, and how much heat it can leach from. And that's why it has to be from 0 Kelvin. There is no cooling. There is no, oh, I'm cooling the place. You are just leaching the heat away. So cold area is basically means how much you can pull from this. Like it's a water pump. You're like, sucking it. So if you dump one in a good system, you should be able to heat at least 3 units of heat from here and then dump it into the environment. So this is the fundamental essence of your heat pump or your refrigeration system or air conditioning system. So how efficient this DeltaT can be? Well, there are two vectors to it. First is the machine itself. For example, what is the compressor you have? For example, the refrigerator compressor is this. Not very efficient. It's not designed for heavy loading. It's designed for turn it on for a few minutes and then turn it off. It's not powerful enough. And again, it has too much friction. Compare that to rotary compressor that you buy in your room. It has lower friction and it has a higher duty cycle. It can work for hour without dying. And then you have big puppies, which we call scroll compressor. So if you have like a giant AC system, whereas 5-6 rooms are being cooled by one AC, then it will have big orange puppy. Generally they are orange, not necessary. You can find black also. That has scroll compressor into it. And that puppy has zero friction. It's like, it just works. And that is designed to tank almost 3 to 4 hours of continuous use and then turn it off for a few minutes, or maybe even run for hours. And then you have a big daddy compressor, which we call turbo compressors. Those chiller size systems, those are 100 tons, 500 ton unit. They have just a shaft, it's basically a turbo pump. You have seen car turbos, it's exactly that. That's the compressor of it. And it works non-stop. It's bro, I turn on, it takes hours to turn on, and then I'm on. I am working and I am cooling down a building. So that is your fundamental efficiency of the work, because it's super easy to calculate the electrical input. You do not know how much electrical work is being converted into actual compression. So this requires a bit of mess. On top of that is the refrigerant. Each refrigerant has its unique signature. Some will work at very low temperature, but it will be very inefficient. Some will basically it can cool down to lower temperature. It just can't leach enough heat. Some would be I cannot cool down enough, but I can easily take enough heat. So there is a lot of mix and match. Now humanity did a stupidity in this. For example, in 1850s we started with logical refrigerant. We had ammonia, we had propane, we had butane, we had carbon dioxide, and then we went stupid and it's okay, but those gases are harmful, so we're gonna create a poison which we call ozone burning holes, and then we use it and then we burn hole, and then rich people are okay, let me milk the dumb population, so we're gonna create a new refrigerants which a government has to pay for, and then we're gonna become rich, and then we have to shut it down because it's burning hole in the ozone. It's wait a minute, again, it's technically not in ozone, this time it's a greenhouse effect. That's why normal refrigerant says that greenhouse potential. It's yeah, and what we are doing now, going back to the same thing. Now it's ammonia is the best. We started with it. Carbon dioxide could work. We had it. Propane and butane, we always knew. It's we literally circled back through 80-50. That's so hilarious. So based on your compressor, based on your refrigerant, there will be a theoretical limit, right? How much work can be done. That's your baseline. That's what people will certify it on. In ideal scenario, this is what you can get. Now here's the deal. You will never achieve that in real life. Why? T delta. That depends on basically delta between your condenser and evaporator. For example, if the temperature lift, basically how cool is your evaporator versus how hot is your condenser, is 35 degrees Celsius of lift, you are looking at 4.4 COP, coefficient of power, meaning if your compressor consumes 1 kilowatt of energy, electrical energy, it can leach 4 kilowatt of heat. Very efficient. Your electrical cost will not be bad. But if you push it to 55, 3. Now for every unit you are only leaching 3. You are literally losing 1 unit of heat per unit of electricity. So, and be mindful, this is optimistic. Generally at 55 delta lift, it's bad. And how do you know the delta lift? You're oh, my AC is set to, let's just say in my case, 27 degrees Celsius and the outside is 48. That's not enough. Outside 48, cool. Condenser, you have to put a probe there in order to know. But here's the deal. The evaporator is much chiller, as in evaporator could be as low as minus 18. That's the gap, minus 18 to, let's just say, 50. That's the T delta. That's the problematic aspect. And you're okay, why do we keep it so low? Keeping it low does give you the advantage. The flow rate is high, as in when you turn on the AC, how quickly it can take a hot Indian room and make it comfortable, that becomes extremely fast. As quick as 3 to 5 minutes, you will feel oh. That's the benefit of having a refrigerant that goes low. Penalty delta is huge. Your electrical bill suffers for it. I can easily see, as India is heating up, I can easily see in the future people are like, yeah, let's use a refrigerant that does not go, because again, as it heats up, we have to run the AC for longer. So getting cool down quick, it does not matter that much. It's like we're gonna run it anyway. So might as well have a compressor that only forces the evaporator only to, like, let's just say 10 degrees Celsius. Anything 10 degrees Celsius, again, it will also dehumidify. It will be a bit slower, but it will be fine. And if it's running all the time, it does not matter. It's just like instead of cooling your room in 3 to 5 minutes, it will take maybe 10 minutes. Because we might the Newton law of cooling, same thing will happen. The first peak will fall off very quickly. So this is the why your delta T matters. And again, condenser temperature and evaporator temperature, both of that has to matter. So for a lot of large industry, they will have very stupid COP. Like you look into a building chiller, it's like COP of 7 and 8. I'm like, how the heck that's possible? Oh yeah, they're cheating. What they're doing is they're running the chiller. It's the best of the best. Some of them have maglev bearings, as in there is shaft is not touching anything. There is no friction. There is no bearing. It's literally floating bearings, magnetically floating bearings. So that is as efficient as it can be. Refrigerant as efficient as it can be. It's just that when they are dumping the heat into condenser can't cool it down. It's like, dude, you're dumping megawatt class heat. I can't cool it down. So what they do? Spray water into it to cool it down, because there is no other way. Otherwise, local temperature of that area will become 100 or 120 degrees Celsius. This will become undumpable. It will stop pulling heat from there. So the only solution is spray water. That's why your data center consumes water. That environment is not cold enough. So that's why you have to spray water into it. Now, to be fair, we do the same thing with coal power plant also to cool it down. So again, environment has to be cold, as in, like, if you do not cool it down, T delta will go down. Basically, the gap between hot and cold, you want to be as minimum as possible in case of HVAC, as large as possible in case of power generation. And this is how your electric bill is affected. This is why putting a data center anywhere does not make sense. It has to be in a place where this environment is low enough that heat can comfortably flow and water is only used in odd cases. Not 24/7. If you do 24/7, you're gonna run out of water very quickly. Don't ask me how I know. Now we come to electronics. This is why I made this video. I was making my linear power supply, my first electrical power supply project, and I just realized moving heat to cold should be easy, right? If my pass element, this transistor, Darlington pair transistor, if this puppy is hot, it should naturally cool down, right? There is surrounded by air, it's not vacuum sealed. So why can't it cool down? Well, it does cool down, but if you have a lot of heat, then it fails. For example, heat has two vectors to it, basically how much degrees Celsius and how much oomph it has. Basically how your electricity has voltage and amperes, and same thing goes for your heat. Heat has degrees Celsius and watt per meter square, how much oomph it has. So if you have a lot of oomph, like this system is designed for 3 amp circuits, so it can still dump like 5 to 10 watts of heat. Like, yeah, that's not much. Yeah, that's a lot if you're looking into the actual silicon that is like 3 to 5 millimeter square. Yeah, that's the problem. This is too goddamn high. So what does that mean? That simply means if you have a basically heat sink, like you must have seen a lot of people have like giant old school heat sink. It's like, yeah, it's useless. If you put a pass element here, the pass element cannot push enough heat into it. Penalty of that is heat is still there. What happens? The temperature of the pass element goes up. This starts to heat up. That's why the data sheet says it has to reach up to 125 degrees Celsius. 125. That's the operating temperature. Otherwise, it simply cannot push heat enough. So this is why your CPU coolers are so complicated. It does not have, it has the flux, like the watt meter square, that could be stupid. Like you must have seen a CPU actual silicon die, that's tiny. That's like barely what, 3 centimeters square, and I'm being optimistic. Let's just say 10 centimeters square. You have hundreds of watt going through that, 100 plus. Like that's my computer, normal computer. Servers and like NVIDIA new systems, those are stupendously, like they are kilowatt in centimeter square. Yeah, so temperature will rise up too quickly if you directly try ambient air cooling. So you have to do forced convection. Best example is your mobile phone. For example, let's just say SoC mobile phone. It's not huge. That's the problem. It's not huge. It's tiny. That's why your display, even though it's consuming more power than your SoC many times, it does not heat up that much. It has such a much larger area. SoC is like microscopic. It's like 5 millimeter square. And that's the plastic box that's 5 millimeter. The actual die would be even smaller. So if you like, okay, I'm going to put a copper tape. Yeah, it has to heat up a lot so it can dump some amount of heat at other end, like 48 degrees Celsius. And benefit, you will not burn, because below 50 degrees Celsius we consider it not a fire hazard. But again, your SOC is cooking, so you're like, okay, what if I replace it with a vapor chamber? Vapor chamber will bring down the core temperature to 56 and the outside will be 55. Your CPU is cool, you will burn. And that's why whenever you look into Apple systems and they have such a horrible thermal throttling behavior, yes, that's the law. They have to do it. You can't expect a metal body, like even in my camera, you can't expect a metal body to heat up so much that it could burn you if a human is supposed to, in normal use case, touch it. So again, that's why your electric stove supposed to heat up. So they are like, bro, we are heating it up as hot as we can. My camera gives you a setting where it's like normal setting, human handleable. Electronics can handle higher temperatures, like, but your hand will burn. But so and it is a high heat mode. It is like, bro, we'll not throttle ourselves, so you can keep recording for longer, but you might burn your hand. So that's why heat has to pile up. The only way to handle it without requiring air conditioning, it's convection. Now, convection fan is the first thing. It's like, even if your air is only taking 2 degrees Celsius of heat, what if you are flowing so much of it? It's like, bro, I'm cool. That's one option. Second option, which is very effective, which is heat pipes. Like a heat pipe is not doing anything. It's dissipating. It's solving one of the biggest problem of heat. You have a tiny element, and tiny element cannot touch the outer element without force feeding everything. It's like heat pipe is like, what if I leach it away? You look inside the heat pipe, it's a liquid system. It's evaporating, condensing, it's traveling. Everything is in motion. So that's why CPU heat sinks nowadays always have heat pipes. That's the only way where you can take a core heat and dump it into the outer edge. So you can have a big ass fan and it's blowing on a big ass radiator. Radiator cannot be useful if it's not leaching heat from the core. So leaching heat from the core is done by heat pipes. And if you want to be like really pro level flex or like server level cooling, you have to use what we call vapor chamber. That dissipates in 2 dimensions very quickly, very rapidly. And that's how you can keep your SoC closer to ambient temperature. That's the target. That's what we are trying to do with computer. We're not cooling them. Like if your ambient is 25, your CPU still would be 60 degrees Celsius. But the target is that delta, 60 versus 25. That we are trying to do. We do not want like, oh, room is 25, but my CPU is 125, like a old school transistor. We don't want that. Or vacuum tubes, they were bonkersly hot. So this is the another essence of it. You have to understand heat flow is not a magical thing. Oh, we have heat, heat will go. That's why like they can't just have data center with a fan running through it. It won't cool down enough. Air does not have enough oomph. That's why they have a chiller that is leaching enough heat. So the SOCs do not heat up. SOC must not cross, let's say, 90 degrees Celsius. You can drive it fast, hotter. Let that be very clear. Lifespan goes down. So generally you want to keep it at, let's say, 80. Or even 75. So you're keeping at that and leaching all that heat away and dumping into air, which you can't dump because again the radiator size would be stupendous for it. You spray water on it and voila, now you know why your local data center is making you dry. So this is the essence of it. And to be fair, we might have a solution. Somebody figured out is like, hey, we don't have that much heat as in like the convection is the problem. What if you have a liquid cooled servers that is not liquid cooled as in like cooling blocks as in like dunk in liquid, and you let the liquid boil. The boiling point of that liquid, dielectric liquid, as in a specific type of oil, is 50 degrees Celsius. What's the benefit? Boiling is a two-phase action. Basically, you are going from liquid to gas. At that point in time, you can't increase the temperature. Temperature gets locked at 50 degrees as long as there is enough fluid. So you have the fluid. Fluid makes sure everything's temperature is at 50 only. It cannot cross 50 no matter how much heat you put into it. And even on a very small, that's why they do not need radiators. They're like on a small die, it's like, bro, it's evaporating. It's physically evaporating. And then you condense that heat. That allows, solves the problem of like taking the heat from the core to a working medium. That solves that issue at least. That could allow, in principle, for chillers to work at much lower throughput. Whereas like, bro, we only need to dump that heat. So. And this was another aspect when I talked about geothermal not working that well in India, because it's hot is not that hot. It's like you are saying 250 degrees Celsius. Again, great amount of it, like gigawatt hour kind of heat. Great. It's just that our cold is not cold. You are showing me a system that works in America that's like average temperature 10 degrees Celsius. I'm like, bro, average temperature 50 degrees Celsius. Hot is not hot enough for us to work. But again, we can still run absorption chiller and voila, we're gonna have AC, which we need. So this is why you have to fundamentally understand what we call delta T. So this was my presentation on the essence of reality, delta T. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my excitement. If you actually enjoyed it, please click the hype button and leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.